I mean, there's.
Testing, 1, 2, 3.
Is it mic 1?
Mic 1, that's right.
Yeah. Okay, cool. I think that's all right. Yeah, let's try one more time. I want to make sure I hear it out here.
Testing, 1, 2, 3.
A little low. Brett, that's your mic.
Microphone.
If he is, too.
I'm going to just start doing all my back-end programming in COBOL. Good reason to do that, though. That's the problem. No one's out there arguing COBOL is the superior language. I really want to get into procedural, that procedural paradigm. Probably going to get thrown away anyway. That bin doesn't show up though. Too much data to migrate. Like they're always just moving. Distributed system. Yes.
I'm Tim Sitnikov.
Tim?
Yep, I
Brett?
talked to you yesterday.
Yeah. Absolutely. Welcome.
Thank you.
Glad you could come.
I hope I didn't mess up your food count or anything. It was.
Yeah. No worries.
Do we pay for this? How does it work?
No. It's we have sponsors.
Okay.
Yeah.
Okay.
Yep. So they provide pizza. People volunteer.
Okay.
So if you want to give a talk, just talk to me.
Okay.
I'm always looking for people. In fact, next week we don't have a speaker right now.
Okay. There's a topic that I'm kind of interested about, and it's about.
Okay.
So basically, diagrams for specifications, that kind of stuff. All the stuff can be done in ASCII and how to do it. So if you want me to do that, how long does it usually last?
Like 40, 50 minutes.
Okay.
Yeah, next week? Okay.
Can do that.
Talk about it after. Okay. Yeah. I'm running this thing. All right. Welcome, ladies and gentlemen. Welcome. Chadev. Is it February 25th edition? Nice turnout today. Yeah. So here we are, and Stephen's going to give us a nice little talk here. Wonderful cover art. Gotta say, it's classic. Next week, working that out. We're working next week's talk out. I think we might have one. It's kind of a weird pattern. Booked out like a full almost 2 months, but couldn't get next week. Nobody wanted next week. It's like everybody hands off on that one. But anyway, I think we've got that. Thanks to our sponsors for providing the pizza and the space, OpenTable and UTC and EPB and help me out here, Andrew. Who am I forgetting? CoLab. There we go. LPG Enterprise Center. All those folks. Thank you, guys. Everybody give a round of applause for our sponsors. It's lovely pizza. All right. Well, I won't kill any more time. Everybody give it up for Stephen. Round of applause for Stephen. Warm welcome. Huh? Yeah.
All right. Well, thank you all for being here. Got a great And for those of you that aren't familiar with OpenTable, what we do is we empower great dining experiences. Generally means we're helping restaurants take reservations, put people on the wait list, manage tables, and that kind of thing. So that's me. It's OpenTable. One of the cool things about working at OpenTable is that it's a global company, and so we're working all over the world. And one of the implications of that is that on a daily basis, as engineers, we're working on distributed systems of a global scale. Which brings us to the topic of our talk today. We're going to talk a little bit about distributing systems and some of the perils and joys thereof. So let's get started. But first, we're going to back up just a little bit, and we're going to say, okay, what is a distributed system? What do we mean when we say these words, distributed system? Well, Leslie Lamport has one take on it. Basically, anytime a computer crashing somewhere that you've never heard of means you're having a bad day, that's a distributed system. Other examples, anytime you use a web page, really, anytime you pull money from an ATM, when, say, you go online to pay your water bill, and you put in your credit card number, and then you click submit, and the website's crapping out on you, and you're not sure if it went through or not, but you don't want to submit it twice, and all of that are some of the joys of distributed systems. We can be a little bit more concrete. Let's say a collection of independent nodes that are working together to act as a coherent whole. Another example of this might be a colony of ants. You have a bunch of ants. They're all autonomous individuals acting on their own, but they're communicating and they're coordinating so that they can do things as a colony and accomplish a single task. Another example might be ticket sales. Let's say you own a movie theater or a concert venue or something like that, and you need to sell tickets. So you might have a collection of ticket booths, and each of these booths would be like a node in your distributed system. And so these booths need to coordinate so that anyone can walk up to any booth and buy a ticket, as if it's one coordinated ticket sales system. And so they need to communicate somehow. There are different ways you can implement this. One way would be, for example, you can have a team of gnomes. So this would be your asynchronous gnome protocol. You give messages to your gnomes, and they pass them between your ticket booths. So now we have our ticket booth gnome distributed system. So now that we have a distributed system, what properties do we want this system to have? What are we looking for? Well, one thing that we want is we want it to be available. What do we mean by available? This is particular nomenclature in the distributed systems literature. And so available just means that at any given point in time, you can always buy a ticket. Somebody can walk up to a ticket booth somewhere and they can buy a ticket. We operate 24/7, 365 days a year to sell tickets. And so we want to be highly available. Okay, it's pretty simple. We've got plenty of ticket booths. So if one of the ticket booth operators needs to take a potty break, no worries. All the other booths can take over. So our system's highly available. Another thing that we want is we want our system to be consistent. What do we mean by this? We mean that the end result is basically the same as if we had one booth. All of our ticket booths are on the same page to make sure that they're not selling duplicate tickets. And so this is where the communication comes in. And our gnomes need to be passing messages back and forth to say, okay, we sold this ticket, make sure you don't sell it. To be a little bit more robust with our consistency, we can teach our gnomes some fancy protocols. We can get their Paxos certification, and then our gnomes can strongly, consistently coordinate our ticket booths. So we tell our gnome, okay, before I sell a ticket, let everybody know that I am about to sell a ticket. So the gnome goes, okay, he's about to sell a ticket. Is that okay? Seat 5B, good. Okay, we're good. Okay, you can sell the ticket now. Go ahead. I sold the ticket. Okay, now confirm that I sold the ticket 5B to everyone else. Okay. The gnome goes, okay, he sold ticket 5B. Got it? Good. Okay, acknowledge. All right, we acknowledge he sold ticket 5B. Great, now we have strong consistency within our system, and we're all good. We're available, we're consistent, we're distributed. It's a good day. So, until we find out that all was not well in distributed systems land. In 1998, Eric Brewer released a paper talking about a theorem that is now known as the CAP theorem. What is this CAP theorem? Have you guys heard of the CAP theorem? Heard of this kind of thing? Yeah? Seen some nodding heads. So we've heard this thing, the CAP theorem, and all this means is that we have consistency, we have availability, but then there's a third thing that we need to talk about, is partition tolerance. And what does that mean? A partition is just a breakdown in communication of some sort. And it means that our system needs to deal with that in some way. So breakdown communication could be a gnome, say our gnome just trips and falls, and his message doesn't get through. That's pretty simple. But it could also mean maybe one of our gnomes is slow, and so another gnome that we send after him passes him up, and so the messages arrive out of order. Or it could mean a gnome gets lost on his way and kind of takes a detour. And so then we say, okay, timeout. We're just going to have to send another gnome and send him with the same message. But then the first gnome arrives also, and so then we have duplicate messages. And so all of these things are things that happen in real networks, and we have to deal with. Now, we could, sorry. Fail. All right. So we could say, well, oh, CAP theorem, back to that. Eric says this is impossible. We can't have all these things. That's the bad news. But we could say, well, no worries. We'll make it so we don't have to deal with partition tolerance, and then we can be consistent and available. Because we can have two of these things, we just can't have all three. And so we'll say we just need to hire a crack team of gnomes that doesn't make mistakes, and they don't fall down. And so then we can have consistency and availability, and we're all good, right? Right. Unfortunately, I'm here to tell you, these perfect gnomes do not exist. The network is not reliable. It's just a myth. It's a tale that network engineers tell their children so they can go to sleep at night, or vice versa. So we have to deal with this reality somehow, that things are not going to be both consistent and available in the face of the network partitions that inevitably are going to happen. So then we think, okay, wait a minute, why are we even distributing? Why don't we just go back to one ticket booth? Then we don't have to worry about any of this problem, any of this impossibility proof, and things will be better, right? So let's say we just have one ticket booth, but we scale it up. And so it's running a really fast Postgres or MySQL book that it's writing its ticket sales down in. And this can actually work to an extent. So for some problems, this is what we do. But there are a lot of cases, unfortunately, where this will only take us so far. You can only scale so far. You reach some hard limits. Let's take the ants, for example. Back to our ants. What if instead of calling of ants, we just want to scale our ant up really big? That would be awesome. So what would happen? Well, besides being terrifying, it just physically wouldn't work. An ant 50 times its size wouldn't be the Superman that it was, where it can lift 20 times its body weight. Now it would collapse on itself and it would suffocate because it's got an exoskeleton and it just doesn't work. The physics just don't work. And so we run into the same types of problems when we try to scale up systems. So, okay. We can't distribute. I mean, we can, but then we run into the CAP theorem. We have to distribute. CAP theorem says we can't have what we want. This isn't good, right? Like this is impossible, but we just need to go back to school and do pottery or something. This is just not working out. So, until, dun-da-da-da, CRDT man comes to save the day. And you might be like, what in the world, CRDT, what are you talking about? I'm glad you asked. So, CRDTs. CRDTs are a way to structure our data to deal with these breakdowns in communication. So it stands for Conflict-Free Replicated Datatype, or the C also alternately can refer to Convergent Replicated Datatype or Commutative Replicated Datatypes. This is an idea, it's a concept that has been coming out of a research institute called INRIA. It's Institut National de Recherche d'Informatique and Automatique. It's a French national research institute that does computer science and applied mathematics and kind of looks at the intersection of those things. So they've been releasing some papers since about 2009 that have been describing these data types called CRDTs. And so we're going to look at these in a little bit more detail. Now, if you're being skeptical, and I hope you are, you might say, wait a minute, you just said that this is impossible, that this whole CAP theorem says we can't have all these things, so what is this snake oil you're trying to sell me that promises to resolve this problem? That is an excellent question. So, we are going to have to cheat a little bit, and that's where we get into the consistent part of CAP. We're going to say eventually consistent. And you might have heard the term eventual consistency. Are you familiar with this term? This is something that's been embraced by the NoSQL community. And so they say, okay, well, as long as we can be consistent at the end of the day, it's okay if we're not strongly consistent in the moment. And this does work out in reality in a lot of real cases. But you might think, well, but in my case, I can't be all loosey-goosey. Like I need, I have important data. Let's say I'm a bank. And so a bank can't possibly just say I can do eventual consistency. I'm keeping financial records. Well, let's take an example of the ATM. So an ATM, it can check your account balance, and it also can let you withdraw, and it can let you put money in. So let's say you have $200 in your bank account, and you go to take $200 out, but at the same time, your wife has your other ATM card. She's on the other side of town, and she is also taking $200 out, and you're coordinating this. And because of a slow network and whatnot, the ATM isn't, it has a little bit of latency in checking your account balance, and so if it wants to be highly available, it's going to let you pull $200 out from 2 ATMs at the same time. And in order to avoid this, they'd have to have their Paxos gnomes working really hard to make sure that everything stays strongly consistent. And so you say, well, of course that's what they're going to do. They can't let you take out more money than you have. You're a bank, you can't do this. Well, in reality, they do. They made this choice a long time ago, before CRDTs were invented, to say that as long as at the end of the day we can reconcile our accounts and we can see that in fact there was $400 taken, then we're okay. We can slap you with a fine. We can make you pay it back. We can deal with it. And so eventual consistency does work for a lot of cases, as long as you're not actually losing information. And this is where some of our NoSQL solutions have gone awry. And they've said basically, okay, partitions aren't really going to happen very often, so we'll just kind of, we'll deal with it. We'll just kind of smash the data together afterwards. We'll use last write wins or something. And that's fine, when it's fine. But when it's not, it's not. And there's some well-known cases of where this runs into problems. There's a series of blog posts called Jepson by a guy named Kyle Kingsbury. Has anyone ever looked at these blog posts? It's pretty good. And so he takes some of these databases and sees explicitly what happens when a partition happens. MongoDB, for example. Anyone use MongoDB? It's a pretty popular NoSQL solution. But he saw with partition, you could lose 42% of your committed writes. So stuff that you thought you had put a permanent record of it happening is just gone, poof, into thin air. And so that's not going to work. It's not going to work for banks. It's not going to work for you. It's not going to work for anybody. We need something better than that. So what do? CRDTs. First, let's look at a few of these terms real quick that might be a little bit fuzzy in your memory. Commutativity. What did we mean by that? All commutativity means is that if we want to say 1 plus 2, we could also say 2 plus 1, and that's exactly the same thing. And so a commutative message, let's say we give our gnomes a commutative message. If the gnomes arrive out of order, it's okay. It doesn't matter, because our operation was inherently commutative. Another property that we're going to talk about is associativity. Associativity, all it means is you can chunk operations. So you can do the 1 plus the 2 first, and then you can add the 3. Or you can do the 2 and the 3 first, and then add the 1. And it's the same results, right? So that's associativity. Idempotency. Idempotency is a third property that is pretty important. And all it means is that you can do something as many times as you want, and it's the same as if you had just done it once. And so an example of this might be you have a light switch that you're toggling, and so flipping down means you're turning the light off, so you slap it down, you turn the light off, you slap it down again, the light's still off, slap it down again, the light is still off. That's kind of an idempotent operation, the downward motion with the hand. So on the other hand, a light switch that's a push button that toggles, and you hit it once, you hit it twice, you hit it 3 times, the light is going to be on or off differently depending on how many times you've pushed it. So that is not an idempotent light switch. So idempotency allows us to deal with the case where one of our gnomes got lost. We sent a replacement gnome. They both arrived. We have duplicate messages. So we want our operations to be idempotent. And so there are, these concepts have been around a long time. But the cool thing about CRDTs is they wrap these operations up together into some predefined data types that we can use to do some useful things. So let's take a look at these real quick. The first one we'll look at is a GCounter. So this name GCounter is referenced in an INRIA paper from 2011. And so if you're interested in these CRDTs as well as others are all explained in great detail in these papers. But so a GCounter is simply an increment-only monotonic counter. And this is basically how it works. let's say we have our ticket booths, and this is general admission seating. We're just going to keep track of how many tickets we've sold. And so when we've sold our first ticket at ticket booth A, we send a message to all the other booths. We said, ticket booth A, 1 ticket sold, and we send that gnome off. And then we sell another ticket, and we say, ticket booth B, 2 tickets sold, send that gnome off. And then at the same time, ticket booth B is doing the same thing, sending his gnomes off with these messages. Now, if these gnomes, because this is asynchronous, we're just going to assume that these gnomes arrive in random order. In the worst case scenario, they all arrive at once, say. And we have to make sense of how many tickets are sold. And so all we do is we just take the maximum. So we look at all these and we say, well, even if this guy arrived first, he's got the highest number. So we take the max here, 3. We take the max here, 2. And then we just add these together, and we see that altogether there are 5 tickets sold. And so at the end of the day, we're gonna see this. And so and at both booths, they're going to get the same result once they've had at least one example of each gnome arrive. So it's pretty simple, right? And it allows us to be strongly eventually consistent. But you might think, well, what if we want to refund a ticket? Then we need to send another gnome out that says 2, but, well, poop, that's not going to work because we're doing a max. And so we can't go backwards. This is a grow-only counter, which is useful for some things, but it's not useful for everything. But, thankfully, there's another CRDT we can use. They call this a pnCounter. And all we do in this case is we just have 2 GCounters. We just have a second GCounter that we designate as negative. And so then we have our negative gnomes that we send out with these negative messages. And all we say is when we refunded a ticket, instead of sending a gnome with a 2 out, we just send an additional gnome with a 1 out. And then we refund another one, we send a 2 out. And then we just add all these together, we subtract these out, and we get our final result. So by combining these CRDTs, we can end up with something slightly more useful. So, okay, let's build up from there again. The next CRDT we'll talk about is a G-set. Oh, thank you. There we go. Yeah, consistency. My clicks are arriving out of order. There we go. All right, thank you. G-set. So a G-set. This is basically it's just a set that is grow only, kind of like the GCounter. So a set is basically just a bag, or we could say we have like a magic hat that we put things in, and we only have one example of each thing in the hat at a time. So we can put something in twice and we only have one thing. That's just part of the set, right? And so we can combine these sets by just taking a union. And so in this first set, so we put a rabbit, and then we put a wallaby. And then in our second set, we put a rabbit also, but then we want to put a Pikachu. And then our merge operation that combines the results of these would just say, okay, we have rabbit, cool, we have wallaby, and we have Pikachu. Awesome. It is idempotent, it is commutative, it is associative, all good. Only catch here is we can't remove anything from our set, because then if we send another message that says, I actually didn't want Pikachu, I don't know how that happened, we just have rabbit. Well, we combine that with the earlier message that had Pikachu, we do a join over those, and we still have Pikachu, and so we can't get rid of the stupid Pikachu from our set. And this is frustrating, and so we have to make another CRDT. And this is called the 2P set. So this stands for two-phase set. And you might guess that similarly to the GCounter, when we expanded on that, we're just going to have 2 sets. We have an add set and a remove set. That's our 2 phases. So all we do is in our remove set, we put Pikachu in that set. And then when we combine these, our end result is going to be just the rabbit and the wallaby and no Pikachu. So there, we can add things, we can remove things. But there's still a problem with this. What if we change our mind and we decide we like Pikachu after all, and we still want Pikachu? We can't add him back to our add set because he's already in that one. And he's already in our remove set. And so, and because we're doing a join over both of these sets, we can't pull anything out of them individually. And so how do we remove him again and then add him again? Well, there's a CRDT for this. So it's one a little bit more complex, but more useful. Call this the observe removed set, or an OR set. So the only change here is we just use unique tags on everything. So when we put a rabbit in, we say this is a rabbit, but it's rabbit 001. And we put our wallaby in, we got wallaby 002. And the key thing here is our Pikachu. Our Pikachu that we put in was Pikachu 004. And so then when we need to remove, instead of just saying we are removing a Pikachu, we say, oh, my slide got cut off. This is Pikachu 004 down here that we removed. And so we label him by name. And so then if we want to remove a Pikachu, but then want to re-add one, we just give him another unique ID, and we call him Pikachu 005. And then he can go back into the add set, and we can add things, and we can remove things, and everything's happy. So these are some basic CRDTs, and they get more complex than this, but within the scope of this talk, we'll stop here, because we can already do some useful things with these. And if you're interested, I encourage you to take a look. You can just Google INRIA CRDT, and you'll get these papers. But let's look at some more less magical, practical examples of what we could do with these already. So let's say we have a social graph, which means we have Facebook, and we're trying to build a Facebook, and we have people, and we have relationships. And so we can model this as a graph. We have nodes, and we have edges, which are the relationships. And so this could be an observe remove set. We have an observe remove set for our people, for our nodes, and for our edges, for our relationships. Or we could use another CRDT, which is called a graph CRDT, which kind of incorporates this and expands on it a little bit more. And this is described in the same papers. It gets a little bit more complex, but it's pretty straightforward. And so that's one example of something we could do. With our basic GCounter that we started out with, that would actually work just fine for keeping track of web page visits. You have a web page that's distributed across a bunch of servers, and you want to get an accurate count of your visits. You could use a simple grow-only counter, because no one's taking back a visit. That's not a thing. And so you're just incrementing, and then you combine all those increments, and you get a consistent and highly available count of all your web page visits. Another example is a shopping cart. You have a shopping empire, and so you're working across thousands of servers. Somebody puts something in their cart, and then they refresh and they put something else in, and they've hit a different server. And so you have to keep this all consistent. An OR set works great for that. You can do a few tweaks to make it more performant, but this particular example is discussed in the INRIA paper of like how you would use an OR set for a shopping cart. But it really works pretty well, just this observe remove set that we just talked about. And then a final example would be your Facebook again, and you have a like button. You just need to keep track of all the things people have liked, all the things they don't like. A 2P set would probably work fine for that. Or once again, there's a U set that is just a slight variation on this. But so the point is that you can take these predefined CRDTs and apply them to your situation in such a way that you can describe your data so that it is commutative and it is immutable, and you can be available, and you can be consistent, and you can go home happy. So CRDTs, you can bust cap, and that's all I have. Any questions? Yeah? It's a good question. So
Repeat the question.
I'm sorry, what is the implementation status? So these are, there's not a plethora of implementations of these at the moment, but there is SoundCloud, who's been having some financial trouble recently, but they have developed a set of CRDTs that are open source that they use, is called Roshi. And so they have some CRDTs you can use. There's also the REAC database. Incorporates some predefined CRDT types that you can use within REAC. There's also, at OpenTable, we're currently working on a framework for working with these CRDTs that we're hoping to open source within the next year. But a lot of times you do implement it yourself, and there are a few reasons for this. One is that you want to push this all the way to your client. This isn't something you want just buried in your database generally, because then your client can take part in your network. To make that more concrete, like at OpenTable, we take reservations online. We also take them on an iPad, which is sitting on a host stand. And so when someone calls in or they walk up, they want to take a reservation, this iPad has become a part of our database. And it has some vital information that needs to stay consistent, but partition tolerant because it's on flaky restaurant Wi-Fi. And so that means that, okay, you need to be doing this in your iOS app as well as in your, like in your server. And so you want it to be down to your client. But, question? Yep. So, good question. So the read operations, ideally, you're doing this at your client. And so you combine these sets right at the client. So like the ticket booth A, when he wants to get a total count of the tickets, he is doing his read operation by, at that moment, combining his sets of ticket booth A and ticket booth B. So the message passing is basically, it's kind of outside the scope of the CRDTs themselves, but the cool thing about this is you can use just about anything to do your message passing. You can just spread the messages everywhere so that everyone has them, because it's okay if you get duplicate messages. And so you can also use a NoSQL database to keep these idempotent messages. And so you can safely use like MongoDB, for example, because you're never having to update anything. As long as you're storing these immutable, not changing messages, and that's the form of storing your data, you can use pretty much any form of available storage to store it. That's true, yeah. And so, so you would want to, like in your source where you're creating a message, you'd want to have some local durability there, or at least like, make sure you've gotten the message out somewhere before you consider it done. And so you'd still want some sort of local durability. It just doesn't need to be a coordinated durability like you would need for, like making a commit in Postgres or something. You can just kind of have a local cache, and then whenever you're reconnected, the message gets passed.
Going back to the 2P set with the Pikachu
Yes.
and the rabbit and the wallaby.
Mm-hmm.
So the tags get generated, yeah. Oh, okay, two more. Actually, wrong one. Maybe the OR set.
Yes.
Yeah.
Mm-hmm.
So the tags get generated at the client because you
Yes.
want all that to happen. So tag collisions?
Great question. So there's a couple ways to deal with this. Generally, you might want to, within a particular client, you can append, or within a particular node, you can append your node ID, so you're kind of namespacing your tags. And so that would be one way to stay consistent. Something that we do is we use kind of a time-based unique ID. And so we combine a timestamp that is monotonically increasing along with our node ID and push that together into UUID, and so we use that. And so then even if you have a node that reboots and it forgets everything, it can still keep making unique IDs. And so that's worked pretty well for us. But it's definitely something that is important to solve when you're doing this. I'm sorry?
Are you using this instead of?
So we use message queuing systems also. And so this actually works really well because let's say you're using Rabbit or something. Like Rabbit sometimes drops messages, and so that can become a pain to sort out when your Rabbit's gone down and then you lost some messages. And if those messages aren't safe to retransmit, then it's really a pain. But if they are safe to retransmit, if you structure your data like this, you can just go ahead and shove everything back through the queue, and you're good to go. So it actually works really well in conjunction. Mm-hmm.
This is still kind of new, so
yeah, absolutely.
I'm trying to think through it. Seems like this works really well for counting amounts of things and like relationships of things, like the sets.
Yeah.
How would this work for like updating an email address where two different clients are kind of fighting each other? Like, where it's not a number or a set.
Yes, that's a good question. There are ways to do it, but it does get a little bit more complicated in that now time is kind of important to us. If two clients are simultaneously updating an email address, we have to make a decision somehow about which one wins. Now, one way would be to say we just keep both, and our merge operation is just adding, and so then we're just using the set when it's colliding. And but on the other hand, when you want to modify, you name. We have these unique tags, and so you name specifically what you want to modify because you have observed it. But sometimes you haven't observed the same thing, and so you have changes that are conflicting. It depends on your use case, but like with email addresses, you might want last right wins for that particular field, and so then you do have to deal with time to some degree if that really is kind of the semantics that we're looking for in real life. And so there are CRDTs that combine a last right wins element in such a way that we get semantics like that while still not just losing data outright in most cases. But so I don't know if that totally answers your question. But they don't fit perfectly with every use case the way that, at least not the way that we usually think of them. But usually we can adjust assumptions to make it work. Yeah.
Does this a lot more data to the client, and the client
So yeah, it does increase. Oh, I'm sorry. Yeah, the question was how much does it increase the load on your clients? And so it does increase it, and really that depends on the shape of your data. And so for our use cases, it works quite well. Like say you have a reservation, and you're probably not making 200 changes to this reservation. You're going to make like 3. You're going to change your mind. You want 5 people, and then you want 6 people, and then you want 7. That's about it. So that's not an order of magnitude change in the amount of data. If you do have something where you're going to have tons of changes, and so you're going to end up with a whole lot of data, you're probably going to want to include some sort of kind of like garbage collection. And there are ways to do this. In some of the later INRIA papers, there's specifically one called TreeDoc. And in TreeDoc, they use CRDTs to implement basically Google Docs. So you want to edit a document. And so to test this, they simulated using their algorithm with Wikipedia. And so because Wikipedia has all these record of changes, And so they said, okay, let's go to a really popular article that's been changed a ton, look at all the changes, and see what would happen if we used this tree.doc CRDT to do this. And with a lot of changes, they said, okay, we're running into pretty large data sets. And so they introduced a garbage collection mechanism that allows them to remain consistent while still having a manageable amount of data. So that is, for a lot of use cases, that is something that you'll have to address. Any other questions? All right. Thank you.
Thank you guys for coming. We have some announcements, right? Andrew? Tom, are you around? Yes. Come on up here. Why don't you go first?
Oh, thank you. Hi, everyone. My name is Tom. You saw me a couple of weeks ago. I wanted to remind everyone that the Ruby Meetup, monthly Ruby Meetup, is happening tonight here at 7 p.m. in this space, maybe right over there on the other side of the divider. If you guys want to come out and have pizza again for a second time today, you're welcome to. It will be me giving a very brief talk on the same topic that I touched on very briefly for the lightning talks, which was testing non-Ruby things with Ruby tools. And I'll see you guys there if you're there, and if not, shame on you.
Thanks. So we've been meeting here since October, and we were kind of one of the prototyping activities for the space in the Innovation Center. And so we've kind of been along for the ride since the beginning, and we're finally having a open house / kind of launch party for the EDNI Innovation Center. That is March 3rd. It'll be the entire building. I think it starts at 5:30. So you can see what's going on each floor, all the businesses that are here already, some of the plans for what's coming next. And it should just be great fun, drinks, food, all that sort of thing. And you all are definitely a huge part of the community that this building serves, and we'd love to have you there. The other thing that I wanted to mention real quick, from Justin, the guy that runs the Python meetup, he works for a company called Emma up in Nashville, and we have someone else. There he is, from Emma here today. There's two of them that work here in Chattanooga. Emma and Eventbrite are hosting an event called Tech Tennessee, and it's a cocktail event. Justin's interested in having 3 or 4 or 5 folks go up there to that. The date, and I think he was willing to drive. The date, crap. Thanks, phone. The date is Wednesday, March 16th. So if you know Justin in Slack, it's JUZTEN. Reach out to him if you're interested in that. It would be great to have, some cadre of folks from our community up there hanging out with the Nashville folks. I think that's all I've got. So March 3rd, 5:30 here at the EDNI. March 16th, 5:30 in Nashville at Emma's office, I believe, for the Tech Tennessee social hour. And you have somebody for next week, or we still need a speaker?
Do we have somebody for next week? Tim, are you going to talk? Tim's going to talk to us next week. Give Tim a round of applause. Yeah. Topic will be announced shortly. Thank you, guys. We'll see you next week.